All right, so the last thing we're going to do in the class for this week is we're going to look at how to use all our knowledge of binding energy and calculating binding energy to actually calculate the energy released in a nuclear decay reaction, such as this one over here, which is producing alpha particles. So just like we did before, you're going to apply Einstein's E equals mc squared. And instead of calculating the mass defect in an atom, you're going to actually calculate the mass defect in the entire reaction. Okay, so if I look at the products and I look at the reactants and I can see the mass defect between them, that will tell me the amount of energy that would be released. The change in mass is going to give me the energy that's released. So we have to go about calculating the mass defect. Now, usually on exams, they'll give you the actual rest mass of the nucleus of each thing, just to save you some time. So they would tell you that radium has got that, okay? And then this is not A, this is N, radon, okay? It's going to be that, and then alpha. All right, so then all I got to do is take the reactant mass and subtract it from the product masses, and then I will get my mass defect, which is 0.0052 U, or atomic mass units. Then I can apply that fast trick that I showed you guys, where you take the atomic mass units and multiply it by 931.5 mega electron volts, and that would tell me that for every atom that undergoes a decay, it's going to release 4.84 mega electron volts of energy. And what we need to remember is that all energy that's released from that reaction is released as kinetic energy of the particles. So they fly off with that much kinetic energy. And since the reaction is producing two particles, a large one and a small alpha particle, they're going to go in opposite directions because momentum is going to be conserved. The momentum before the explosion is zero. So the momentum after the explosion is also going to be zero. Often you'll see in the text that at this point, I can take that energy, I can try to calculate the momentum of each particle and the velocity of each particle. I want you guys to take a look in the book at some sample problems like that, because they often appear as well. How would you go about calculating the velocity that these particles fly off with after calculating the binding energy? I'm not going to show a video of that. I want you guys to go and do some research on that. So again, calculate the velocity of those particles after you find out that 4.84 mega electron volts is supplied as kinetic energy.